Okay, good afternoon everybody, and welcome to the next session on audio coding. So today is the continuation of psycho-acoustic models, where I stopped before Christmas, remember? So we found that we need a mapping to the Bach scale for our psycho-acoustic model. So this is mimicking what the ear is doing. The ear has basically a built-in filter bank with unequal bandwidth, where the bandwidth becomes larger when we go to higher frequencies. Our MDCT filter bank has equal bandwidth, and the same the FFT. Right? So when we take the FFT, for instance, as our input with the equal bands, and we want to compute the psycho-acoustic masking threshold, and we want to have a precise masking threshold, then we need to simulate what's going on in the ear. And for that, we also need to simulate this unequal bandwidth. And for that, we need to have this Bach scale mapping. This mapping basically is a nonlinear function from linear frequency to a warped frequency in such a way that we collect more of our MDCT or FFT subbands into one Bach band if you go to higher frequencies. Right? And this mapping from the linear frequency scale to this Bach frequency scale is what these functions are doing, which we are describing now. So this goes from the linear domain into the Bach domain. So here's the function mapping to Bach scale, and it produces a matrix for doing so. So I implemented such that we have a matrix, and this matrix just collects a number of subbands from the FFT or MDCT output into one Bach band. And the higher the frequency, the more bands it collects into one Bach band. Yeah, and since I try to avoid for loops for the processing, I just produce a matrix in the beginning, and then this matrix is doing the job of the for loop instead. So this function produces this matrix, which we set up in the beginning. So here you can see we have 64 subbands in the Bach scale. So basically, we take more bands in the Bach scale than the Bach scale itself. So basically something like a third Bach that we use here for our subdivision. And we construct a matrix W here, which is doing this mapping. And this matrix W has ones, entries of ones, at the positions where the subband fits to this Bach band. Right. So this is done here in this for loop. So here you can see we assign so we assign ones where it fits to the Bach band. So here you can see this is actually a true value. So if round by bin Bachs divided by step Bachs equals I, right? So I is the corresponding subband in the Bach domain, then it sets a 1. And this is because the true value equals a 1 in Python. So that's kind of a programming trick here. So when this loop is done, then it simply returns this W. And what it's doing can be seen here in the next picture. So you can see it. So here on this horizontal axis, this matrix corresponds to our subbands. So here I just took part of this matrix. I just go up to 256. It actually goes up to 2024 or 2048 here actually, because we have double length for the FFT. And here you can see on the vertical axis of this matrix, you have the Bach bands, the Bach subbands, which now goes from 0 to 64. So you can see for each subband, at some point there's the corresponding to the Bach subband. So if we now take our subbands coming from the MDCT or the FFT and multiply them as a column vector from the right-hand side, and you can see that its output, the range of the FFT subbands which are within a certain bark band are added up in output for this particular bark band. So after multiplication with this matrix, we obtain 64 subbands in the bark scale. Does that make sense? So this basically does the mapping, this nonlinear mapping from the linear frequency scale to the bark scale. So here you can see this function which does the mapping. And since we have a stretch of ones, basically all the subbands within this range are added up. Right? So here you have the magnitude coming out from the FFT, from our signal, and then the power of all, or the magnitudes of all those subbands are added together to form one bark subband. And that's why we have many fewer bark subbands as we do have FFT subbands. So basically we lose information. So observe, this is not invertible. Right? So this goes only in one direction, from the FFT subbands having 2048 subbands to the bark scale having 64 subbands. Right? But here we also don't want to invert it because this is just for obtaining the masking thresholds. Yeah. Right. So for each such 1/3 bark subband, we have the signal powers from the corresponding DFT subbands. And then we take the square root to obtain voltage again. So this is what we can see here. So here again we have our W matrix. And here this n frax is basically our Nyquist frequency, which I input here. So we only use it up to a certain frequency. Then here this mx is the magnitude of x, which comes from the argument of this function. And here we do the squaring of it. So this would be taking the square of each magnitude subband of the FFT before we multiply it with this W. And then after the end, after this matrix multiplication, we take the square root. Right? And this way we go back to a voltage or current again. So this is then the function doing the actual mapping of the magnitudes. So the function before was creating the matrix, doing ones at the beginning of the processing, and this is done every time a block is processed. So this function has to be fast. Right? And that's why this does not contain any for loop. All this is doing is actually this line here, when you look at it. All this is doing is squaring multiplication with this matrix and taking the square root of all the values. And this is really fast. Right? Matrix multiplication in Python is really fast. So that's why we can do this function for each block without much delay. Yeah. So after we did our processing in the bark domain, we also want to go back. We want to apply the quantization then in the linear domain, and that's why we need to go back from bark to linear. So after having computed the masking threshold in bark scale, we need to map it back to the linear scale of our filter bank. For that we need to distribute the corresponding power of each of our third bark bands into the corresponding filter bands on the linear frequency scale, so that we're able to apply quantization accordingly. So then we take the square root to obtain the voltage again, and we again construct a matrix to do that in Python for speed. Right? So when there is a 1 subband in the 1/3 bark scale, it gets a factor of 1. If there are 2 subbands, they get a factor of square root of 2 and so on, using a diagonal matrix multiplication for those factors. So this is because we want to keep the energy, right? If you have an energy into 1 bark scale, we want to keep this energy even if we distribute it over several linear subbands. And that's why we need to scale it to the point. So if there's one subband for one bark band, then the energy is the same anyway. But if we have one bark band, say at the higher frequencies, and this one bark band corresponds to two linear bands, then we basically need to subdivide the energy from this one bark band onto those two linear scaled MPCT subbands. Right? And that's why we need to have the square root of 2. So if we have the energy, we divide the energy by 2, then basically this is a factor of square root of 2 for the voltage. Right? Remember, voltage is square root of power. So that's why we have those factors here, to keep the energy conservation basically. Yeah, and this is then done here at this little function for constructing the matrix for going back from the bark scale to the linear scale. So you can see it. Yeah, actually this is the W, the matrix which we already constructed. Here's the LFFT, the number of FFT subbands, and here you can see we have this matrix product. Here's the W again, and we're using sum of W on the axis 1. This is the number of entries for each bark band. Here we sum them up and take the square root. This is exactly what's done here. So here we get the factors. Here we have the matrix itself transposed, and then we return W inverse. Right. So this constructs the W inverse in quotation mark, because it's not really an inverse matrix. It's just used for inverse mapping. And this matrix looks like this. Right. You can see it's indeed basically a transposed matrix. But here you can see it's getting lighter colors when you go down here. And this is because we have more linear subbands in them, so the power is distributed over the longer stretch here. So it's thinner because we distribute the same power over a longer, higher number of subbands. Make sense? So other than that, it's just the transpose of the forward transform. So here, if we multiply this matrix with the color matrix of our bark subbands, we get this higher number of subbands, the 2048, for quantization in the MPCT domain. Make sense? So this basically allows us to go back into the linear domain. So this matrix again is constructed once at the beginning of the processing and then reused for each block. Yeah, and then this function is used for each block. So all this matrix, all this function is doing is this matrix multiplication that you can see here. So basically, here you can see it. This NP dot is the matrix multiplication. Here, this is the magnitude in the bark scale, and here is this matrix that we just saw. And here this n-frax is the Nyquist frequency, depending on the sampling frequency here, transposed. And then we just return our magnitude in the linear domain. Make sense? So basically, just going back to the linear domain. Yeah, now we can apply the threshold in quiet and our spreading function. Right. So on top of our adaptive masking threshold, we have the threshold in quiet. We have an approximation formula from Surfside Digital Audio Signal Processing, that's his book. And the approximation for this level of threshold in quiet is called LTQ in dB, and in Python notation, that's this formula. Again, there's no secret behind this formula, it's just an approximation. Right? It's just fitting this formula to the observation. We can plot it here in IPython. So here I'm creating a lin space from 20 Hz to 20,000 Hz in 1,000 steps. And then I'm just applying this formula. So f is in Hertz, So f divided by 1000 is in kilohertz. So we just this formula. And then I can plot it in the semi-log x. Plot semi-log x means that the x-axis is logarithmic, which again makes sense because of this arc scale characteristic of our hearing. Here I limit the axis again. Here I put labels on it and a title. And what we get is this. So here you can see the logarithmic x-axis. You can see the exponents are equally spaced. Then you have changing width here. You can see here the higher frequencies grow faster in this semi-log x scale. And vertically you can see the dB scale. And this shows the ear has the maximum sensitivity acquired at this point. Right. So what frequency is this? How do you know? So when you go from here, down here, what is this? Can you recognize this point?
15,000.
So this is how much? 10 to the third is how much? See? It's not that easy, right? So 10 to the third is 1000 hertz, right? So what is the next marker? 2000, right? And this one? 3. And this one? 4. Yeah, so it's somewhere between 3 and 4 kilohertz, right? Yeah. Kind of odd, but that's the way how it is. Right? And also when you go to higher frequencies, so here, this is 10 kilohertz, right? 10 to the 4, 10 kilohertz. And then, let's see, the next, this would be 20. Right? Just taking the same width here. So this is a factor of 2, so this is 20. And here you can see, basically hits a wall at around 16 kilohertz. Basically there we have a very fast increase in attenuation. Not quite as steep here at the low end. This should be, I think, 20 hertz. So 20 hertz is also not very sensitive. But this is in quiet. So this is basically the sensitivity of our ear if it's totally quiet. So this is basically the maximum sensitivity we get out of our ear. But since most of the time we have an audio signal, this is just a fallback solution. Right? Usually it will be dominated by our spreading functions. Yeah, so the dB of the formula is for sound pressure that we just saw. Our internal representation has plus minus 1 as a full scale, which corresponds to 0 dB. Right? So 1 would be 0 dB. Assume we play back our audio signal such that full scale appears at the sound level of speech, which is about 6 dB, so that's a comfortable level actually. Hence, to convert the sound level of our internal representation, we need to reduce the threshold of quiet by 60 dB if we take our internal normalization to 1 being the full level. Right? It's a difference of about 60 dB. So this is what we need to take into account for the threshold in quiet. It's kind of tricky. This threshold depends on how loud we turn up the volume. Right. So if we make the volume very high, then the threshold would go down because we can hear more. Yeah, so even with an audio signal, the masking threshold in quiet still matters at the lowest and highest frequencies. Right. When it really goes up high, there it will be higher than our spreading function at those boundaries, the edges, the very low and the very high frequencies. So this is where our threshold in quiet matters most. So we then combine the signal-dependent masking threshold, the spreading function, and the threshold in quiet by taking the maximum of the two at each frequency. So most of the time our spreading function will dominate, but at the ends, highs and lowest frequencies, this threshold in quiet will dominate. In Python, we clip the result to avoid overloading and where problems and correct our masking threshold using these commands. So LTQ is LTQ flipped between -20 and 60, and we shifted 60 dB down. Right. So here we assume that we don't have very loud signals, and -20 is less loud than we can hear anyway. So this is basically adjusting for cranking up the volume. And then we do this downshifting to account for our internal representation, the internal normalization to one being full scale. Yeah, so we can now test our approximation formula for our hearing threshold in quiet by producing noise below this spectral threshold and listen to it. If we don't hear the noise, it works. Right? We could produce noise shaped like this threshold, and our ear shouldn't hear it if it works right. So we can use the program. We can use the Python function in our program masking quiet demo.py, which is called noise from the dB spectrum. And maybe I can just open it. So I made a little demo here for testing, which is this. Oops. Copy. And open a terminal shell. Open a terminal. Plus. Gedit. Paste. So here you can see the Python program. And this is what you can also find in Moodle 2. So this is intended for you to try at home. Maybe with headphones or the speaker in your laptop. It should also work. And here you can see this function, noise from dB spectrum. Its argument is spec, which is a desired spectrum. Fs is the sampling rate. And it then produces noise which is shaped like this spectrum. Right. So here, this is the argument. First plots the argument. Then, this is a dB scale, and then it turns this dB scale into a voltage here by this inverse dB function. And it produces 40 blocks of sound here in this for loop. So here this M goes from 0 to 39, and here I'm producing a random sequence. You can see random values. These random values are distributed between 0 and 1, but audio is usually centered around 0, and that's why here I'm subtracting 0.5, so that I have equally plus and minus. Then I multiply this by our desired spectral voltage, and since it's supposed to be a power, just because of scaling here, so now it's between -1 and 1. And here I multiply with this desired voltage, so now this is our noise spectrum. So now I have a spectral representation of our desired noise. Here I'm concatenating it with zeros to make it suitable for the inverse FFT. So basically this noise spectrum is going specified from 0 to pi, which is pi is Nyquist. And we know in the FFT domain, pi to 2 pi is a negative frequency, so it's just a flipped version of the lower frequencies. But instead of producing the flipped version, I just appended the zeros and then take the real part of the inverse FFT, which gives me the same result. So here I have the noise in the time domain. So Here we can plot it in the time domain, and finally its output using the sound function. Sound.py is also in Moodle. Did you all see it in Moodle? Sound.py. So I'm using it all the time. So this is the function, and then we just need to call it here in the main section. We can also use this function somewhere else. That's why I have this if main, because if we import it, then this is not executed. Yeah, so here sampling frequency is set, number of subband is set. Here a sample spectrum noise, so this is flat. I have ones, 1024 ones at 60 dB. So that's the speaking level, clearly audible. Here I'm doing the correction for our internal normalization. Here I have an announcement using eSpeak. So eSpeak is this robot voice in Linux, right? Text to speech. And then I have this noise created and played back. So this robot announcement is always good if you have a sound example, because if you don't have a plot, you have nothing else to show. Yeah, and then I do the same with the threshold and quiet. So now instead of taking the ones, so here I took the ones, now I'm computing LTQ. Right, here F is the link space, LTQ is now the threshold and quiet, this formula here. Again adjusted. And now I can see here noise from dB spectrum. Now we have LTQ instead of spec at the same sampling rate. Again, preceded by this announcement of the robot voice. So what we should or expect to hear is, first time we hear white noise. Everybody knows how white noise sounds like, right? Do you know how white noise sounds like? It's like, remember? That's white noise. So how should this LTQ sound like? What do you think? Maybe I can try an active speaker here, see if I get it to work. Yeah, what do you think? How does noise shaped like the masking threshold, like the threshold and quiet sound like?
Bluetooth mode. FM mode. Bluetooth mode.
I'm not sure if this is working. Sound settings. Hardware. No, it's not working. Strange, no? Oh, I have a little bit.
Front, right.
Yes.
Front, left. Front, right. Front, left.
Okay. So any idea how noise sounds when it's shaped like the threshold and quiet? Any idea? Should we hear anything? Yeah, theoretically we should hear.
It's lower than threshold.
Huh?
It's lower than threshold.
Yeah.
Yes, or we can hear it.
No, if it's below the threshold we cannot hear anything. Threshold below the threshold means it's audible. It's inaudible. It means it's weaker than the threshold. So if the signal is weaker, you cannot hear it. But if the power exceeds the threshold, it becomes audible. Right? So everything below the threshold should be inaudible. So going back to this picture here, right here you can see the dB number, and when you go down it means less power. Right? Here you have minus 20 dB, 0 dB, 20 dB. Right? So when we go up, we increase the power. Make sense? So if this is the threshold at which we hear something, then adding more power at the same frequency makes it more audible. But if it's below, then it's inaudible. If this is the threshold at which we can hear something, then being weaker, having a weaker signal, we can hear even less, right? Well, if this is barely audible, then this becomes inaudible. Make sense? If not, you need to ask me.
It's clear.
Huh?
It's clear.
It's clear? Okay. So how much stronger is 20 dB compared to 0 dB? What factor? How much power more do we have? 100? You know, why 100? Yeah, basically because power is 10 times log base 10. So if you have 100, log 10 of 100 is 2, 10 times 2 is 20, right? So this fits. So 20 dB is 100 times more power than 0 dB. Same 40 dB, right? 40 dB is 100 times more power than 20 dB. It's because dB is a logarithmic scale. Okay, so now we can actually try it. So Python, let's see if Python 3 is working. So remember, the first time we expect to hear a clear white noise, like this hissing noise, like, right? But the second time we expect to hear nothing, if the masking threshold is okay, if the threshold implied is okay. So let's try it.
Now see and hear white noise with flat spectrum.
Flat spectrum. So here is the shape, the spectral shape. It's flat in frequency. Right? All frequencies have the same power. So the number on the x-axis is the DFT subband number. This is the produced noise signal in the time domain. So here you can see how white noise looks like. So we can actually also zoom in, and then you see fast wiggling here. See, it's still fast wiggling. And now you can see a little bit more detail. So this is how white noise looks like. Basically, each sample is totally independent of the previous sample. Right? It's like throwing a dice each time you produce a sample. Some random number.
Now see and hear noise shaped like the threshold in quiet approximation.
Yeah. Did you hear the noise? So this is the white noise. So now we have the same here, but shaped like this threshold in quiet. This now looks a little bit different, right, than the picture we saw before. Why does it look different? It looks distorted, right? Why? Right, because now we have a linear scale, right? Yeah, before what I showed you was on the semi-log x, right? This is not semi-log x anymore, and this is how it looks like when you have a linear scale. Then actually this part, which looked nicely tilted in the previous picture, now looks extremely steep, right? And this part, which looked extremely steep in the previous picture, now looks less steep. And this is because this is now the linear scale coming from the DFT subband numbers. Right. Okay, so This is now the time domain noise which it produces. Here it looks almost the same. Let's move in and see if we find a difference. Yeah, this looks different, right? Interesting. So when you actually zoom in the time domain, you can see a clear difference. Why is that? Why do we have this difference now in the time domain? It's also noise. We started with random numbers in the frequency domain, and now going back in the time domain, we see clear correlations between those samples. Any idea?
So white noise.
No, this is not white noise anymore. This is non-white noise. This is noise shaped like the mask, like the threshold required. So remember, white noise was basically each sample was totally independent of the other samples. It was like throwing a dice each time you want to have a sample. Here, you see a lot of similarity, so it almost looks predictable. And it's like slow changes. You have a pattern, you have an evolving pattern. So why do we have this evolving pattern here? What do you think? Well, it's basically because of the spectral shape. Right? When you have independent samples, that also means you have a flat spectrum. But if you have a non-flat spectrum, and we just saw we have a very non-flat spectrum, that means we have basically a filter operation. So you can take this spectrum that we just saw, and instead of multiplying the noise with the spectrum in the frequency domain, we can take the same noise in the time domain and convolve it with an inverse transformed spectrum domain, which then becomes an impulse response. You can take this shape of the of the threshold required, apply the inverse DFT, and then you have coefficients in the time domain. Make sense? So then you have basically the impulse response of a filter which has this frequency response. And if you have a filter and you filter noise, that means you create correlations. You take neighboring samples, multiply them with factors, and sum them up. And that means neighboring samples obtain correlations given by the coefficients of this filter. And this is what we see here. Right? It's basically filtered white noise, and filtered white noise has correlations. As soon as you apply a non-trivial filter, you will get correlations between neighboring samples. And you get such patterns here. Does it make sense? So this can be explained with filter theory.
So there is always correlation between neighboring elements in time domain. It's not white noise.
Right, exactly. So did you have filter theory? Digital filter theory? So did you have impulse response being the inverse DFT of the frequency response?
Yes.
So yeah, you can. What you learn is you have the impulse response, and if you apply the DFT, you get the frequency response. Right? Like if you have a low-pass filter, you take the coefficients of the low-pass filter, apply the DFT to it, and you get the frequency response of this low-pass filter. Like we did for the MDCT. Right? Every time we applied Frexi to analyze our filters in our filter bank, same for PQMF filter bank. Every time we apply the Frexi function internally has an FFT. So we take the coefficients of our filter, zero pad them, add more zeros to get a higher resolution in the frequency domain, then apply this is correspondingly longer DFT, and we get the frequency response. Remember? Frexi? MDCT? not that long ago. PQMF. If not, you should take a look at it, because this is basically coming up everywhere. So this is basically the effect of filtering we get here. Right, we have a signal, we filter a signal with a filter, and that basically means we convolve it with the impulse response. And this DFT is basically inside the frequency function that we use for analyzing our filters. So let's close this. Oh, nothing happened. That was quick. So you could hear nothing, right? So actually that was correct. So let me try it again.
Now see and hear white noise with flat spectrum.
So this is white noise.
Now see and hear noise shaped like the threshold in client approximation.
So that's that. Could you hear something? Huh? There were some clicks, right? But the clicks were artifacts from blocks that I used. So the clicks are actually no problem, because they're not really there. They are phantoms. But besides the clicks, there was nothing, right? So basically we had the same power of noise, but now it was completely inaudible. So I think you can also see it when
Now see and hear white noise with flat spectrum.
So here you can see 0 dB noise. And
Now see and hear noise shaped like the threshold in client approximation.
yeah, so here you can see it's altogether a little bit lower power because it starts at 0 dB. So it's not quite the same power. But still, it's the same order basically, hopefully. And it's shaped such that it's hidden basically. So here you can actually see the power that comes out. So here you can see that it's distributed roughly between -0.2 and +0.2. So it's actually quite a similar power than the white noise. But still, we don't hear anything from it. Gone. And this is basically the same as the 13 dB miracle that you heard in the beginning of this lecture series. Remember? The 13 dB miracle? So there it was shown that the noise can be hidden below the masking threshold. Here I just showed that the noise can be hidden under the threshold of quiet, right, without any signal present. Yeah, so it works. Our noise shape, according to our threshold approximation, is indeed inaudible. So that's nice. And it also shows you should always check what you did, because most of the time it doesn't work. Here it just works because I already tried it out. Right? So this is proven. But in general, if you come up with something and program it on the first time, it never works. Yeah, so this leads us to our complete psycho-acoustic model. So here you can see it. So in the beginning, I set up the two matrices for the mapping to and from the bark scale. Here this W and the W-inf. And then I have this function masking threshold, and it takes as argument the magnitude from the MDCT, the MX, then the two matrices W and W-inf, then the sampling frequency Fs, then the spreading function matrix. Remember, this came out of our nonlinear superposition. Then alpha, which is also this exponent for the nonlinear superposition, and NFFT is the number of FFT samples or subbands. Yeah, so input here mx is the magnitude spectrum of a DFT, in our case size 2048, and it returns the masking threshold as voltage for its first 1025 subbands, and this is such that it fits to the MDCT with its 1024 subbands. Right. So you can see mapping to BARC is the first step here. Then here's the threshold calculation in the BARC domain. Here it uses the spreading function matrix from last time. Now I'm going back, mapping from BARC using the WINF matrix, going back into the linear domain. Here I'm constructing our threshold and quiet, which we just saw, and then I'm computing the maximum of the thresholds. Here's the masking threshold from the spreading functions, and here is our fixed threshold and quiet. So I'm taking the maximum of the two. And here this is the dimension along it computes the maximum. And then it returns this empty. Does it make sense? So at this step you should understand each step of this code. If not, you should ask me. So this should be straightforward by now. Yeah, so here's an example. Here I have now an idealized spectrum, just to show what it's doing. So for testing, it's always a good idea to start with a very simple input, such that it's predictable what the output is, and so that you can compare your expectation with what you really see. So here you just have a single active subband in the FFT. Subband number 200 is active at 20 dB. Right? So this is an ideal sinusoid in this subband. And then you can see, after computing our masking threshold, the blue line here is what comes out of our model. Does that make sense? So here you can see it's actually a combination between the threshold and quiet, which is this, and the spreading function caused by the sinusoid, which is this. Right? And because we took the maximum function, here when it grows above the maximum of the threshold and quiet, here we get the spreading function. And you can also see the spreading function, which is less steep to higher frequencies and steeper to lower frequencies. So why does this spreading function now has this staircase function? Staircase form. What do you think? So far we saw it nice and smooth, like this, but now we have a staircase. Why do we have a staircase?
Because that wasn't Barclay and this is
Yeah, exactly. So basically, we computed this, the spreading function in the BARC domain, and for each BARC subband we have one fixed values. Right? In this case, 1/3 BARC gets the same value. We don't distinguish different frequency inside one BARC scale. And this is why we get the staircase, right? This is going from one BARC to another BARC. Or actually, if we have like more subbands in one BARC, then we can see like here, then all the same subbands which fall into one in the same 1/3 BARC subband get the same value from mapping back. So this is basically also a consequence of the BARC subbands becoming wider when we go to higher frequencies. Yeah, so actually this looks good. So here you can see the top of the spreading function is at some distance from the peak of the sinusoid, and this is the simultaneous masking, remember? So simultaneous masking was the distance from the signal peak to the beginning of our spreading function. So this distance. So here you can see how much simultaneous masking do I have here? Can you see it? How much simultaneous masking? So it actually goes from here to here. Yeah, roughly 40 dB. And for tones, this makes sense. So 40 dB. 40 dB is usually more than enough. So here I'm a little bit on the conservative side. But it makes sense. So 40 dB simultaneous masking here. So this picture makes sense. It seems to be working. We can also take a look at the complete demo. So I have this psycho-acoustic model.py. So maybe we can take a look at it. Copy. Gedit. Site model. So here you have the complete model, and you should also take a look at it from Moodle. So it's also in Moodle, and this basically tells you step by step how psycho-acoustic model works. Right, so here, first function is just doing what it's doing, spreading function much. So this computes the spreading function in the bark, in dB, and it uses the number of filters and the maximum frequency, computes the spreading function prototype in the bark scale. So here, this function just creates the spreading function prototype at some given frequency. So you can see I always commented everything nicely, so that it's more easy to understand. And this is also good practice, because after a while you forget yourself what it was good for, right? And then it's important to have comments. So this is the spreading function itself. Here the spreading function matrix, it takes this function and puts the shifted versions of it into a matrix, again to avoid for loops in the block processing. So here it constructs the spreading function matrix. Then we have this masking threshold in bark, which is doing the nonlinear superposition. Here, the nonlinear superposition with the spreading function matrix. Here, it's doing the threshold in quiet. Here, actually, in the bark subbands. So, slightly different than in the demo that we just saw. Here, it's applied in the bark domain. Here, it's computing the maximum, and then it returns the masking threshold. Yeah, here the function, just the formula to go from hertz to bark and from bark to hertz. Here, the matrix for mapping to bark, and then the matrix from bark, which we just saw, are both here. Yeah, and then mapping from bark. So this is the actual mapping back. So here you have the mapping forward to the bark spectrum, and here you have the mapping back to the linear spectrum. So that's basically it, and then I can apply this function to example functions. So first, you can see I define my constants, the sampling rate, the maximum frequency, the alpha, the number of filters in the bark domain, and the number of filters in the FFT subbands. Right? So this is made that you can also change it if you want to try out what happens. Then here I'm setting up my matrices for processing, as we just saw. Then here I'm computing my spreading function based on the signal. Right. Spreading function matrix. Here's the spreading function matrix, which is displayed. Here I'm starting with a test sound. You can see I'm using noise. Here I'm using the noise in the time domain. Again using random numbers, but here rand n. Does anybody know what rand n means? Rand n is normal distributed noise, like a Gauss distribution. Right? So by default this is centered around 0, and that's why I'm not, why I don't need to subtract the 0.5 here. So I play it back and then I do the processing here. Here I'm computing the magnitude spectrum, then I'm doing the magnitude bark. Here I'm computing the masking threshold, going back to the linear domain, then I plot the result. And here's another test signal, a tone. Here's a sinusoid instead of noise. Play it back, and here I'm doing the same computation of the masking threshold and plot it. Yeah, that's it. And then I can run it. Yeah, questions to the code. Does the code make sense so far? Okay. So, let it run here. Python 3. So again, this is my matrix for mapping to the bark scale. This is the matrix from the bark scale. This is the spreading function in the bark scale. You can see here the slopes. Here steeper towards lower frequencies, flatter towards higher frequencies. And here dB scale vertically. Here is now the matrix of the spreading functions. You can see each row or each column consists of a shifted spreading function. So again, that I can apply the spreading function as one matrix multiplication. Yeah, so this was the noise. And here you can see the resulting masking threshold. So here blue is again the white noise in the spectrum. Here's the FFT subband. And you can see orange is now our masking threshold. So what do you think? Does that make sense? This masking threshold for noise? Think about what it means. It means any noise below this threshold should be inaudible. So if we decide to add noise up to this level, it should be inaudible. Do you think this could be? What do you think? What do you think? Does this picture make sense? No idea? Huh?
Masking threshold should be above that.
Why?
Because there will be audible noise.
Yeah, this is audible noise, but this should be part of your signal that you want to hear anyway. Right? So this white noise might be a piece of a music. Right? Sometimes you have white noise in music, right? So you want to keep hearing this white noise. But you don't want to change this white noise. Right? If this is part of music, you want to keep this white noise as it is. It should sound the same. So if you put this masking threshold above, that means you could add the same noise without hearing a difference. Right? But if you have the same noise and add the same noise, basically then you double the power of the noise. And I guess that's something you can hear. If you increase the power by a factor of 2, it's like cranking up the volume by a power of 2, and it's probably audible. Here we add almost as much noise, but less than a factor of 2. So if we have this noise given, and we add more noise, but slightly less than what's present already, maybe a factor of 1.5 or something, then you could argue that's something that's in order. If you just turn up the volume of noise a little bit, then maybe it's in order. Make sense? And this is because noise plus noise is kind of inconspicuous. Right? It's because noise is already there. If you add some more noise, it's not so hard to hear. It's not so difficult. It's a little bit hard to hear if you add noise to noise. And that's why this masking threshold can be high. Right? Because it's already noise. It's not like a sinusoid where we have 40 dB difference. Yeah, when you look at it, how much difference do we have between, say, this upper peak and this masking threshold? It's maybe, I don't know, 5 dB. Can you see it? So you just look at, yeah, it's a little bit wiggly here, but imagine this is like the noise level here at the top, then you're at 65, and the masking threshold is a little bit below 60, so you could say here this distance is maybe 5 dB. Right. And this is actually what we saw as simultaneous masking for noise masking noise when we looked at psychoacoustics. Remember? Noise masking noise, we had something like, I don't know, 6 dB. And this is what we indeed see here. Right? We see this 5 to 6 dB simultaneous masking. So that makes sense. But that also shows you need to know the simultaneous masking for noise and tones in order to see if this works. So what's simultaneous masking for tone masking noise? Well, I mentioned it 10 minutes ago. Already forgot what I told you 10 minutes ago? It's 40 dB, right? So memorize it. This might be a question for the test. Here we have roughly 6 dB. So that's simultaneous masking noise, masking noise. So these numbers are worthwhile to memorize because they are the basics of psychoacoustic models. Yeah, what about this peak in the beginning here? Why does it have this peak here, this steep peak? Should it be there, or is it a bug? Think about the threshold required. Right? So basically, this is the leftover of the threshold required towards the very low frequencies. So it's not really an artifact. It's basically left over from the threshold required. Or not left over, this is what's showing up here from the threshold required. Yeah, so this is now the tone. So you just heard the tone. And here you can see the resulting masking threshold. Maybe I'll make it a little bit bigger. So again, here's the tone at something 200. So this time it's actually a real tone that you just heard. And here you can also see the simultaneous masking. So again, let's check. Here we can see it. So here I put my mouse on it, and when you look here in the lower right hand corner, you can see the precise coordinates. So here x is 200 and y is 80. 80? It's hard to see. The number is too small. It's 86.9, so it's 87. So here's 87, and then we go down here. and we have 57. So 30 dB in this case. 30 dB is also okay for simultaneous masking. Right. So here you can see the simultaneous masking, and here again is your spreading function from this sinusoid. And now you can also see that this threshold in quiet has those step functions, because in this case I applied the threshold in quiet in the bark domain, unlike before. And that's why mapping back you get those steps. And here you can see you have wide steps at those high frequencies, because here the bark subbands are much wider than here in the low frequency end, where the steps are really narrow. Yeah, so this also makes sense. So that seems to work. Yeah, then I have more demos. Here's a demo with quantization. Right. So this is now applying also quantization in the subbands according to the masking threshold. So remember, the masking threshold was there such that we are able to hide quantization errors or quantization noise below the threshold. So the noise that we want to hide comes from quantization. So that means we need to use the masking threshold to determine how big the quantization step sizes can be in each subband in order to avoid audible distortions. So this is what I did here. This one here. Copy. Gedit. Yeah. So here, this is doing quantization, and here I'm actually using the MDCT, as you can see here. Right. So the MDCT, and it uses the psycho-acoustic model and quantization. And you can see it as an input. It uses the audio signal X as a sampling frequency Fs. FB is the filter bank, the DCT window, MDCT window. N is the number of subbands. N fills 64 is the number of the bark subbands. Quality setting allows me to shift the threshold. It's a little bit above and below what the model computes. So quality 100 means it uses the original masking threshold. Yeah, so here it's doing the usual computation. Computes the matrices. And now it goes on to compute the MDCT. So here there's actually a default sign window if you don't specify it. And then here you compute the analysis filter bank, the MDCT. And here I'm using the function that we already saw as a fast implementation using the matrices. Right. So here then this contains the subbands. Here's the number of blocks in the signal. Then here this computes the short time Fourier transform of the signal, here X. So this goes in parallel. So this computes the MDCT, and this computes the short time Fourier transform of the signal. So this is important for the psycho-acoustic model. So the psycho-acoustic model does not take the MDCT as input, but here the STFT with 2048 subbands. Right. Here it computes a correction factor here. This correction factor is important to get the correct powers. So I just found this is good for fine-tuning to have this correction factor here. Then here I'm doing the masking threshold calculation. Oh yeah, this correction factor is basically to make the power from the STFT comparable to the power that comes out of the MDCT. Right? Those powers need to be comparable. Yeah. So here we have the processing starting for the number of blocks. So here it goes over the blocks, and for each block it computes the psychoacoustic model. Right? So here we can see YS, W, the colon stands for all the subbands, and M is the block number here. So here you can see those sequences compute the masking threshold for this block. And so here, finally, we have the masking threshold for this block. Yeah. So after we did that for all those blocks, we have basically our masking threshold, and we turn this masking thresholds to a quantization step size delta. Here, just squaring, then drop the last STFT because that's Nyquist frequency which we cannot use in the MBCT. And then here we do the quantization. You can see here, this is mid-thread quantization. So here we take the Y that's coming out of the MBCT and divide it by the deltas which are computed from the masking threshold. So this shows you how to connect quantization and masking threshold. Yes?
Question. Like here the quantization is uniform, right? So if we want it as a non-uniform quantization, what do we need to change for the YQ, like NP1 while dividing the delta, or?
Yeah, like in the lecture, right? So if it's non-linear, if it's non-uniform, you need to apply a corresponding non-uniform function. Remember, you have mu law. This is the usual. It's basically a logarithmic function. So look at one of the early lectures where you can see the detailed description. So basically, it's some sort of logarithm that you would apply to the y before dividing and rounding. So basically you apply the uniform quantization after some non-uniform function, and after dequantizing you would apply the inverse function. But that's actually some of what you should have in previous lectures. So look at the early slides and also take a look at the Wikipedia pages for it. Or maybe at ADSP. I describe it in more detail in all slides on ADSP. Did you have ADSP? No?
I have it, that's not here, like it's different courses that we have.
Which are you on MCSP or AudioCoding? MCSP. Yeah, for MCSP you should have had ADSP in the first semester.
Yeah, we had it, but it was in Russia, so people don't understand.
I
It's
see.
different for.
You're from Kazan? I see. Yeah, that's a problem, right? Yeah, so this is uniform quantization, and what you get here out of this function is the quantized MBCT values together with a masking threshold. And then here basically you have the decoder, the MBCT synthesis, and the dequantization. So it takes as input the quantized subband values and the masking threshold. And you can see here you have the dequantization of the masking threshold. So the masking threshold itself, let's see, is represented as empty bar quant. Where's empty bar quant? Here. Can you see empty bar quant? So here it's initialized with zeros. Then it's gone. No, here. Okay, here it is. So when you have a coder, you also need to quantize the masking threshold. Right? It's not enough to just quantize the signal values from the MDCT, but you also have to transmit the masking threshold itself to the decoder for the dequantization process. Right? And this is what you can see here. And this is also done in a way that is usually done in audio coders, that you apply the quantization on the exponent. Right? So you write the masking threshold as 2 to some power, and then you quantize the exponent. So this is what you see here. So you have 2 to the mt bar quant. So there's some scaling by 4. And then let's see. Right. So here we have the log 2 of mt bar quant, and this factor of 4 is basically the size of the quantization step that you apply here. So you multiply by 4 so that you basically get quarter exponents after rounding. Right? And you also limit the range by clipping, so you only have a certain number of bits for those exponents which you can use, so you also need to apply clipping. So here, this also makes sure that the dequantized is at least 1. You don't want to have smaller values. Here I already do the dequantization. So this dequantization is then also used in the decoder. And here I'm also using this dequantized value here in the mapping from bar. So this is basically a little bit like the encoder and the decoder and the encoder. So here, again, we take this empty bar quant, the quantized exponents of our masking threshold. We compute the empty bar dequant, the dequantized values of our masking threshold. And then here we set up the matrices for going back to the linear domain. Here we map from the bark domain, we apply this mapping from the bark domain to the masking threshold here, empty bar dequant. And then we are back in the linear domain, and we compute our quantization step size from it in this way. And here we do the dequantization, just multiplying quantized values with the step sizes delta. Right? Yeah.
Wouldn't it be way easier if we just, because those whole matrices, we have to kind of send them to the decoder, so we have to code them. Wouldn't it be easier to just code delta and give it to the dequantizer and not those whole matrices here?
No, the matrices are computed in this function, the W.
Yes, but we need the values.
Yeah, the empty bar quant.
Exactly.
This
And
one.
then
This,
the W inverse. We
no,
also
this is
need
computed here. This is computed
Okay.
here.
But still, wouldn't it be easier to just transmit delta?
Basically, you could. It's just a matter how you save bits, right? And that's why this transmission is using this exponent. You could also indeed have just some form of delta, but basically would end up the same thing. Because you want to spend the bits in such a way that you minimize the number of bits, but at the same time be precise enough to represent the threshold. So basically yes, but then you would twiddle again with those factors here to get a good range, and you would end up with the same representation. Because this representation is basically being like a masking threshold for the masking threshold, for the quantizer. Right? And this is not done using a model, but it's basically trial and error. People tried the exponent and found it makes the most sense, and then how many steps do we need in the exponent? Turns out quarter exponents is good. So, but indeed, it's just a linear connection. between the delta and the y's. So here you can actually see delta and mt is just a factor of 2. Right? And the multiplication of 2 is actually no problem.
But we could just skip all those steps before if we just the delta.
No. It's those steps you need anyway.
Yeah, but we did them above.
Yeah.
So we're doing them twice.
You don't like this multiplication as 2?
No, all those steps in the for loop. Some things we're doing twice. So mark dequant we're computing twice. The inverse we're computing twice.
No, this mark dequant is computed once, but it's done in the encoder and it's done in the decoder.
Yes, exactly.
Yeah.
That's what I mean. That we're doing the same steps in the encoder and in the decoder.
Yeah.
That's what I don't understand.
So, yeah, but you guess why it's done. So this is basically such that the encoder uses the same masking threshold values as the decoder. So when you do quantization, the step size is based on the masking threshold. And if you would use the original masking threshold for the encoder, but in the decoder you use the dequantized values, then the masking threshold would differ. The original and the decoded masking threshold, they differ in the quantization error. Right? And that means you would have an additional error. And this is what you want to avoid. And that's why also the encoder uses the quantized masking threshold. It doesn't use the original masking threshold, but it uses the quantized threshold for its quantization. So here, mapping from bulk MT, and then here this delta comes from the dequantized version. Right? And we want to make sure that this delta and the delta in the decoder is the same. So just to make it in synchrony, we need to have this dequantization also in the encoder. Otherwise, we won't have different values. That's the tricky part. Does that make sense to everybody? That's actually a good question. Every time you do quantization in an encoder, you have to make sure that this encoder uses the same values that also the decoder uses, which means the encoder also needs to compute its results based on the quantized values, which means it also needs to dequantize it. And it's called a decoder in the encoder structure. Make sense to everybody? This is actually quite similar to predictive coding. If you want to predict a value in the encoder and decoder, you have to make sure that the predictor in the encoder has the same dequantized values as the decoder in order for the two getting to the same result. So there's actually no way around doing this dequantization here. I mean, there is a way, we could omit it, but then we get problems with the decoding. Decoding would be a bad quality because you would have to drift between the two. Yeah, so this makes sure that we have the same delta in the encoder and the decoder, so that we don't unnecessarily increase the quantization error. So here's then our dequantized values, and then we take the dequantized values and apply the synthesis MDCT to get the reconstructed signal. See, here I have an audio example. So actually I'm using the WAV file library to read in some audio file. So you can see it. I read in this file here, this test file. It can be anything, also something you recorded yourself. And then it goes through the steps. So here you can see it computes our window, sine window. Here it's doing the encoder part, MDCT with quantization. Here it's doing the decoder part, the dequantization and the synthesis MDCT. And then it plays the original, and it plays the reconstructed after dequantization. And ideally, they should have the same sound. So let me quickly play it. So this is now almost a complete coda. Python 3.
Original signal. Reconstructed signal after quantization according to the masking threshold.
What do you think? Could you hear a difference?
No.
Could you hear a difference? Yeah, because when you're closer, you actually hear more difference. When you're further away, you hear fewer differences. And here you can see, this is actually what we just talked about. This is the quantization of the scale factors. Right? So you can see the scale factors here are on this range between 10 and 70. I'll make this a little bigger. And you can see, indeed, they have discretized values. Right? And you can also see how they change, evolve over time. So these are, I think, the 64 scale factors for the 64 bark scale subbands. Right. Yeah, and this is the quantization indices of the subbands. You can see here, indeed, they're actually rather small. Right? So you can see most of the time they're between -3 and +3. So how many steps is that from -3 to +3? 7, right? 3 plus 3 plus the 0, so 7 steps. So that means we can use just 4 bits. No, actually less. 3 bits. Right? So we could get by with 3 bits for all the subband values. 3 bit per sample, it's not that bad actually. Just applying psychoacoustics. So this is the spectra. An example of one block. So you can see in blue is the magnitude of the original spectrum. It's not visible because it's hidden by the spectrum of the reconstructed signal error. And red is the magnitude spectrum of a reconstructed signal. So here you can see red is actually the spectrum for reconstruction. And you can see here most of the subbands are actually 0. Right? There's actually not much left from the signal. So why is most of it 0? Because there's so much below the masking spectrum. And that means we can actually indeed remove this stuff without being audible. And this is how we save the bits. All those gaps which we don't transmit saves a lot of bits. And so it shows actually we can save a lot in the spectrum using psychoacoustics. And that's also why the signal error hides nicely the original spectrum, because the error is as big as the signal itself. So when you look at this spectrum, it's kind of amazing how little difference you could hear. Right? Because the spectrum looks totally different. Right? So all what's left is those few peaks here. So here's some peaks, here. Isn't it amazing? So little of the spectrum is left, but still